Dr. Abhiram J, Assistant Professor at Sir M. Visvesvaraya Institute of Technology. Born and brought up in Bangalore, Dr. Abhiram is an alumnus of National College Basavanagudi, where he completed his Bachelor of Science between 2009 and 2012. He went on to pursue his Master of Science at the National College Jayanagar from 2012 to 2014. Between 2015 and 2022, Dr. Abhiram carried out his doctoral research in the domain of glass sciences at Visvesvaraya Technological University, Belagavi. He was guided by Dr. Rajashekara K.M., professor at SJC Institute of Technology, and Dr. R. Raja Ramakrishna, senior researcher at St. Petersburg National Research University, Serbia, Russia. He has served as faculty member and coordinator in the Department of Postgraduate Studies and Research in Physics at National College Ayanagar from 2014 to 2023. Later, he joined Indian Academy Degree College, Henner, and currently works as assistant professor in the Department of Physics at Sir M. Visvesvaraya Institute of Technology. During his doctoral work, Dr. Abhiram focused on studying the nonlinear optical properties of dichroic glasses doped with gold and gold-silver bimetallic nanoparticles. He continues this passion for research through a seed grant project on microwave synthesis of bioactive glasses. Beyond glass sciences, he has ventured into polymer science, nanoparticle studies, and electrode deposition. He also conceptualized an innovative Android application titled Batch Matrix Calculation, designed to support stoichiometric calculations for materials science research. With over 19 Scopus indexed publications and a registered patent, his contributions to science are remarkable. His citation score stands at 133, with an H index of 6 and an I-10 index of 3. Apart from research, Dr. Abhiram enjoys writing science blogs that transform complex physics concepts into relatable, real-life case studies. You can explore his insightful writings at abphy.in. Dr. Abhiram J, a passionate researcher, educator, and science communicator, inspiring curiosity through glass and beyond.
Thank you very much, Ram Krishna. Actually, I cannot say no to you because you are my classmate as well as you are my good friend. So that's where we have that connect. We have a bondage since National College days. So without wasting much time, let me start my presentation. So I would like to close my video in order to avoid the technical glitches. So whenever I think of this subject, glass science, I think of another Ramakrishna. His name is Dr. R. Raja Ramakrishna. He is my supervisor, guide, who was also my colleague in National College, Jayanagar. So without him, I wouldn't be presenting whatever I'm trying to present today. So it is his efforts and his guidance that led me to deal or led me to get into the world of glass sciences. So now it's my pleasure to invite all the audiences of Prajna Foundation to just show few of my ideas that I had with respect to glass sciences. So welcome to the world of glass sciences. So the word glass, it is not something new. It has been used as kacha, ranjika in the world of Sanskrit, as well as vitrium from Roman. Mako and Elifaku is from the Mesopotamian civilization, and gel was usually coined during the Indo-European trade, which later turned into glassen, and finally we have the word called as glass, which we are trying to use. So the word glass comes from Proto-Indo-European trade. That's where it was actually the etymology of glass is being shared. So, if I have to say, the view of this entire glass as such, it is not, it is not something new. It is being since the Vedic era, where Indians were using glasses extensively. Then Thailand and Vietnam, even they were trying to make use of the glass beads. Then we had the major Egyptians as well as Italy, UK, Africa. Okay, the basic natural the salt that you're trying to see, it is from the African belt, especially in the Mediterranean Sea region. So that is where we have this sodium silicate glasses which came into the major bloom, and we have glasses from Russia as well as finally today we have few well established companies like Corning in USA, as well as we have Scott Glass as well as Carl Zeiss, which are from Germany as such. So glass is something which is not new to the entire world. It has been practiced since the Vedic era to the contemporary world. So now these are few interesting personalities that I would like to tell who have transformed and revolutionized glass science as such. So the one whom you are trying to see is Ernst Abbe. We know him. Very few people from the glass community know him as the one who came up with the Abbe refractometer to find the refractive index of glasses. But his contribution is not limited only to the refractometer, but actually there is an interesting tale which I have come across when I was going through the Scott glass. The a guide to glass from Scott. So they have actually mentioned what role did Abe play. Actually, Abe was searching for someone who can design glass, and he found Otto Scott, who is who is a chemist as well as who has been into this field since ancestrally he was gifted with the art of making glasses. So they both collaborated, but he is an academician and he is an enthusiastic chemist. But a physicist and chemist cannot come up with the products without having an industrialist pitching in. That's how Carl Zeiss walked in, and he funded both to come up with numerous problems addressing glass science. And by the World War II, they came up with enormous ideas. Not only that, they started resolving problems related to bulb thermometer. They started redefining the kitchenware utensils. So everywhere, wherever you see the glass started coming up. So when glass started taking up its own uh, feature after Second World War, Abe actually he whatever the profits that he earned out of this glass research, he gave back to Zeiss Foundation, and even Scott gave back his profits to Zeiss Foundation. And they moved apart from Zeiss because Carl Zeiss passed away. And later, Scott established his own firm. And today, if I have to say, the leaders of glass science, we have two companies from the same origin, that is from Germany. One is Zeiss as well as Scott, who are doing tremendous job, especially with respect to advanced optical coatings and optical materials that we are trying to see. Here we have another interesting personality who has revolutionized the ceramic industries as well as glass industries in India. Today, if Indians are working in field of glass science, it is because of him. He is none other than Ishwar Chandra Das Varshney. He established based on Paisa Trust Foundation through Lokamanya Tilak. He came up with the first glass industry in India. Then later they started coming up with lot of glass industries. And not only that, he was also one of the major member in establishing he is the founder president of the Indian Ceramic Society. So he has significantly contributed in parallel to Abe to they are all unsung heroes of glass science. Today, whatever we are trying to see in the world of glass, it is because of Abe, Scott, Carl Zeiss. If it is globally in India, it is it we have to give the credit to Ishwar Chandra Das Varshney. So coming up with the landmark achievements, the glass, as per the records that we have, they say that it is from 3500 BC, but there are few glasses which we had even in our Vedic era. So then we had telescopes from the Galilean world. Then we had glasses which we were able to see from which started replacing the windows, and then we had a lot of glasses, especially once when you're able to see this Pilkington, when they came up with the float glass technique, it again revolutionized glasses, where we have a lot of glass facades being established in the technology. So today, whatever we are trying to see, it has been continuous process. The research in glass is still there are a lot of things that are still the problems are open when it comes with respect to the glass science. So the first thing, before defining the glass, I would like to say that this is the famous. I would like to use the phrase "break the glass ceiling." So if this is being done, then it is not going to be no longer a glass, it becomes the ceramics. So in order to give you an idea what exactly glass is, you can see this, there is an S curve over here. This S curve indicates that this is the rate where it starts crystallizing. So we have to make sure that the material that you are trying to use, it has to reach the molten state, and the moment it is being cooled down, so it has to cooled in the very quicker time. That is why we have this time, especially in this time temperature transformation diagram, we have this time in the logarithmic scale, and it has to be cooled below this nose point. So this dashed line that you're trying to see, it is called as critical cooling rate. So any material that gets quenched, that solidifies before this critical cooling rate, it is bound to be amorphous in nature. And if it is surpassing the supercooling zone, thereby there are more possibility that it becomes a glassy material. So that's how glass comes into the existence. So if it reaches this point, if it reaches this time with respect to this temperature, then there is lot of possibility that it can recrystallize, and thereby it will start forming a ceramic. Or probably what you can do is you can reheat the material at this temperature, so that it again recrystallizes and tries to form glass ceramics. So in order to define glass pictorially, by making use of time temperature transformation diagram, any material that surpasses the critical cooling rate, that surpasses the ceramization rate, and if it is below this nose point, it forms the glassy region, it falls into the glassy region. But to put it in words, ASTM defined that glass is an inorganic product of fusion which has cooled to a rigid condition without crystallizing. And then we have one more definition which supports the ASTM, which further it tries to improvises the definition by glass transition temperature. It says that glass is a non-crystalline solid which exhibits the glass transformation range in the volume enthalpy temperature relationship. And then by clubbing these two definitions, my co-guide Dr. Rajaram Krishna and Dr. Jakrapong, they have defined that glass is an amorphous solid which exhibits glass transition temperature by arresting the kinetics below supercooled liquid region when bypassed crystallization. So it is just giving the meaning to the pictorial representation that I have told you what exactly glass is. Now, having said that, how are glasses classified? If I have to say, the classes are classified as network modifiers, network intermediates, as well as network formers. Network modifiers, they have high coordination number, that is above 6. Network formers, they usually have very low coordination number, that is between 3 to 4. And network intermediates are those which fall in between the modifier as well as the former. So they are like, they are like, this is one party and this is the other party, and these network intermediates are like the janta, where they try to take the role. They tend to move either towards the modifier or former depending on their coordination. So we need, this is the kitchen where we are trying to make the dish. So here we have the elements that are towards the left. They are basically alkali metals and alkaline earth metals, which are usually the network modifiers. And if you are trying to see towards the right side of the periodic table, right from boron, silicon, germanium, phosphorus, arsenic, selenium, antimony, tellurium, all these elements, they fall into the category of network formers. So now we have aluminum as well as bismuth, where they play, in fact, even lead at times, they play the role of network, the intermediates, where they tend to take the role of either getting into the former, they try enhance the for glass forming ability, or they try to modify the network. So, what is the role of a modifier? What is the role of a former? What is the role of an intermediate? This is to be understood in a very simple. This is to be understood very much. So, former basically they are the larger substance which are used usually. Modifiers are used in a very optimal quantity. Okay. So, intermediates they are just trying to connect the bridge. They try to form the bridge, or they try to break the bridge depending on what kind of application you are looking for. It is like when you are trying to cook a dish, for example, the basic, when we go with chow chow bath as an example, we have upma as well as we have kesri bath. The main ingredient that we use is nothing but rava. But we should know what is the quantity of salt that is to be used and what is the quantity of sugar that is to be used respectively. So the role of modifier is very less because you're using the salt quantity very less. Whereas when you're trying to look at the role of intermediate, it is slightly higher than the. It depends whether I'm trying to look at the intermediate in the level of former or in the level of modifier. And when you go with the former, it is the base item. It is going to have the larger composition share that you're trying to deal with the glass system. So is it like, should I use only the boron for the glass? No, we can have the combination of boron silicon. So we have a famous borosilicate glass, which comes up with binary formers, that is boron silicon. Not only that, we do have silicon phosphide systems, we have phosphorus and fluoride systems. These people I have not added up. They are more interesting. They fall into the category of halide glasses. And if you are trying to look at these systems, that is sulfur, selenium, tellurium, they fall into the category of chalcogenides. So I have not added them. They too contribute very interesting results, especially when you are trying to look for glasses for photonics and infrared applications. So as we go ahead, this is the kitchen. So based on this, we need to make the idea on how to come up with the glass. So since the ages, glasses were made using the glass blowing technique. That is the conventional method. But in our labs, we start with weighing the sample, then we try to crush the sample, and then we try to place it in the furnace, and then we have the step process for heating the samples. So we try to heat it up at 150 degrees. That why do we heat it up at 150 degrees centigrade? That is because you need to expel the moisture content in the glasses. Then we try to heat it up at 438 degrees Celsius. That is because we need to expel the halides, particularly the chlorides, from the system, especially if you have some complexes which contain chlorides, we try to expel it when you are trying to set it up at 430 degrees Celsius. Then at 600 degrees Celsius, we try to expel the carbonates. Then at 1050, we melt the system. And the most important thing is how the glasses for R&D is being prepared. And now the other way of preparing glasses is actually by another method where we try to actually I'm trying to play this video. There are some technical error glitch where it is not able to play. Actually, another method is by going up with the microwave oven. Microwave oven technique is actually much more simpler, where you need to, the process is almost similar. The conventional melt quench technique, if it takes somewhere around 2 to 2.5 hours to synthesis glass, the microwave technique, it will try to actually synthesis glass within few minutes. It hardly within 10 minutes you can synthesis a glass using the microwave technique. But there are some challenges. Like you don't have the flexibility or freedom in the kitchen if you're trying to use microwave oven. That is because you need to choose the host matrix which are susceptible to the microwave that you're trying to use. And secondly, you cannot come up with low microwave wattage for glass synthesis. The minimum wattage that is required for microwave synthesis of glasses is, even if I'm coming up with if you're coming up with 700 wattage, your limitations are very low. If you're coming up with 900 wattage, you can explore little more glasses. Higher the wattage, higher the possibility of exploration of glasses from the kitchen. And the third most important thing is, the choice of crucibles. You have to go with only silica or alumina crucibles, which are going to be very much expensive when you are trying to deal with these crucibles. Especially when we go with the conventional melt quench technique, we can make use of the porcelain crucible, which costs hardly 60 rupees. But if I go with a silica crucible, the cost of crucible will be somewhere around 450 rupees. It's going to be very expensive if you're trying to do R&D, especially with microwave technique. And the most important thing is setting up the microwave exposure time as well as managing the thermal stress. These two things are always bound to vary because of the power. And the major thing that we can still hear is there is also one more major this one, if especially if you're trying to deal with glasses where you don't want water content in it. Especially for optical glasses, we always try to avoid the water content in it. So in such cases, microwave glasses are proven to be much more efficient because exactly at 2.1 gigahertz, microwave absorbs water molecules, and there is a strong absorption of water content with respect to microwave, especially if you're trying to use this microwave technique. So further, if I have to say, glasses have been used in the field of civil engineering, especially in the field of architecture. If I have to say, we know that these windows that you are trying to see, the stained glasses that you are trying to see, especially in the cathedral churches, they they come across with, this gives a research problem to two different streams. One is in the civil engineering, as well as it also gives a research problem to explore with the literature, especially the Gothic architecture and Gothic literature. They can come across with why these glasses were made and how these designs were made. They are all made up of stained glasses. So stained glasses are usually doped with the colorants or dopants which give you these bright colors. So especially we can make use of gold or silver or copper or nickel or iron. So they tend to give the color. Based on that color, these glasses are being formed. And we can see that these were the windows up to 1850s. If you see the windows that you were trying to see, they never used glasses earlier. But today, we are in an era where we come up with smart windows. These smart windows, they are going to replace. Even today we are trying to make use of these windows, the traditional windows that we have, where we have a glass with which has been affixed to a wooden frame or a metallic frame. It doesn't try to kill the stray light. So in order to remove the stray light, we have the smart windows. Especially we call them as thermochromic windows, or as well as there is also an electrochromic windows, where we have the liquid crystals which are embedded in between them. So based on the thermochromic laminate, it is based on the temperature, it tries to give the tint, and it tries to make sure that it is opaque in nature. In case of electrochromic, instead of temperature, here it is the potential. Based on the voltage, it will try to uh, change the phase of the liquid crystals and try to create that opaque region. And that's how we have these materials that are being made. So you have a glass as well as two electrolytes. In between, you have an electrochromic material, which is basically a liquid crystal. So this smart windows are going to be the future, especially if there are people who are working in the field of civil engineering as well as in the field of architecture. So you have a problem where you can come up with different kind of the materials, especially with respect to smart windows. Again, there is one more way of coming up with smart windows is by just varying the refractive index. So when you are able to vary the refractive index, you can clear the tint by just again it is by coating a layer of liquid crystals to the same material. So coming up with the material, so you can see this how this electrochromic windows work. So you have this glass framed which has been affixed in the window frame. So uh, when the electrochromic layer, if it is being made, when the sunlight passes through it, the solar heat is being uh, the sunlight is made to enter and the heat is being absorbed by the window. So this is how you can also see that there is the heat gets absorbed, and based on that it tries to form the tinting. And this is one more interesting material which you could have come across, that we call it as glass bricks. Glass bricks are also being found extensively in field of architecture nowadays. And in 1851, Crystal Palace was built in London, but due to some fire accident, this was actually, this entire Crystal Palace, which was made completely by glass, it got destroyed. So that's an unfortunate thing. But we had the glass architecture. This is the first glass architecture that we had, especially with respect to the entire building. If I have to say glass facades, so this is the first glass architecture we had. But when it comes to Bangalore, we had glass house in Lalbagh. We are fortunate we are able to manage it. We are still having the same glass house. Even this is again built in the year 1889, and we have glass facade technology for this. But still, the windows that the smart windows culture is not being seen over here. That can be improvised as and when we come across with the problem. So today's Bagmane Tech Park, or wherever you try to see most of the tech parks, they are made up of these glass facades. Coming up with the next application that we have is photonics as well as optical devices. One of the major revolution that we try to see, especially with respect to photonics, is since the invention of laser. So when laser came into the existence in 1960, uh, where they made use of ruby laser, it is a three-state laser system. The major challenge that we had with respect to ruby laser is, it was not trying to have that thermal decay in it. So they came up with ND-AG laser, which is a four-state laser system. So there they were able to address the thermal decay concept. So within 2 years, Schneider came up with ND glass laser. The only difference that they have between the crystal laser as well as glass laser is, this crystal laser, due to the continuous photonic process, it was generating a lot of heat, and heat dissipation was a major challenge. But glass was able to fix the heat dissipation. But when it comes to the spectral purity of the laser, the spectral purity of glass laser was very much poor compared to the crystal laser. So again, they have their own set of limitations when it comes to lasing applications. But when it became the pulsed beam, ND glass laser was found to be much more efficient than the ND crystal laser. And secondly, the cost effectiveness of ND glass laser, ND glass laser was found to be much more cost effective, efficient than the ND crystal laser. So because it is easily manufacturable, and the cost is also relatively low, and thereby they have their own potential applications when it comes to lasing devices. Then the next important thing is, I was trying to tell you that the stained glasses. So if I have to add any stains, I need to go with the material. I need to go with the dopant. So based on the oxidation state of that particular dopant, I can have the color. So if it is Cu plus 2, I can have the aqua blue color. Then I can get, if I use cobalt 2 plus, I can have midnight blue color. So these are the colors that can be generated in a glassy system by dopants and its oxidation state. Whereas here, the color that you're trying to see, especially with respect to the rare earths as well as with respect to manganese and silver, it is not in the visible region. Whereas these are the colors that are obtained in the visible light, that is due to the irradiation of the visible light. Whereas these colors that we are trying to see, it is due to the irradiation of UV light. That is why I have added a layer of blacky region and then showcased these colors to you. So now, if you are trying to see, especially these glasses, they can be used as waveguides or the light guides, as well as they can be used as moldable optical lenses. And especially when we are trying to look at the LED applications, they are used as the remote phosphor diffusers. Because this is one more interesting challenge that comes with respect to glass science, especially particularly with respect to LED, the sharp illuminescence of those light that needs to be reduced. The intensity of light has to be diffused, and glass plays a vital role, especially the dysprosium glass plays a vital role in giving the spectral quality of the LED light, as well as by diffusing the high intense radiation. So we there are a lot of works that are happening, especially with respect to glass science, particularly in the field of LED materials, where they are coming up with more and more of warm light LED device applications rather than the neutral or white light, cool light LED device applications. So we have these applications. So that is to with respect to the display devices. With respect to the rooftop solar cells, especially the facades where we are trying to see that they are made up of glasses, especially particularly with the vanadium doped glasses. They find also the iron oxide doped glasses. They find potential applications with respect to solar cells. And when we get into the healthcare devices, healthcare assisted devices, glasses also find their potential applications. There are two ways how we come up with glasses. One is by the conventional melt quench technique, where we come up with the bioglass pellets, where we come up with bioglass powders, and then they are trying to come up with the structures, dense glass structures. And other part that we have is the uh, precursor based, the sol gel technique, where we have a solution which has been condensed, and the BG gel, bioglass gel, is being 3D shaped through, after drying it has been 3D shaped to the porous glass structure. And even these glasses, these gelation, it might lead, when we add with respect to the biopolymers, we can also obtain fiber mats using the 3D structure. So there are several techniques to come up with the bioactive compounds, especially with respect to glasses. But with the types that we have, especially with respect to bioglasses, are basically based on the three former groups, which we call it as silica-based glasses, borate-based glasses, phosphate-based glasses. So we have, these are the major requirements. One, it should exhibit the bioactivity. Second, it should have the controlled biodegradability. Third, it should, you know, if these two things are being satisfied, further the third point is it should also try to enable itself to form the porous 3D structure. It should have adequate mechanical strength. So these are the things which are usually used for bone grafting materials. And if you're trying to use for the other part, it should have the drug encapsulation as well as release methods, as well as the entire preparation method has to be low cost, as well as it should be simple technique. And it should also exhibit good elasticity or plasticity. So if these prerequisites are being maintained, then we can see that these glasses, they cater to the different types of applications, ranging from cartilage repair to soft tissue engineering. So there are certain challenges, especially with respect to silica. When we see silica, though silicate is highly bioactive in nature, it is ease of production, especially with respect to melt quench technique as well as sol gel technique, is an advantage to it. The flexibility in shape, as well as coming up with by altering the compositions, is also very much ease with respect to silica. And we can also dope, since there is a flexibility in shape and composition. We do have flexibility in doping the bioactive elements in it. Then it also gives the strong bioglass and bone bond. But there are some demerits when it comes to silicate glasses. When you are trying to deal with it, the major challenge that we have is with respect to the conversion of the BG component into hydroxyapatite layer. This is the most important thing, which we need to observe whenever we come across with the process. So when the conversion is either it is slow or it is incomplete, it partially it tries to form the layer, which makes, which if the glass stays in the body for beyond the 21 day cycle, it becomes toxic in nature. So that is because of the slow degradation rate. And since it is staying over there, it might lead to undesirable crystallization, and this occurs due to poor sinterability of these glasses. And again, these chemical and mechanical performance depends on aging of these samples. So when we come up with the next segment, that is borate glasses. Borate glasses are highly bioactive in nature, and they are also flexibility in shape and composition. They have ease of access to doping bioactive elements. Again, their bond is also strong with respect to bioglass and bone bond. When and what happens is when you are trying to come up with boron substitution, especially particularly in these glasses, they enhance the mechanical properties of scaffold, and the crystallization rate is also reduced when it comes to borate glasses. And since they have very low network connectivity, the hydroxyapatite layer that is to be formed, especially particularly in borate glasses, is very easy. It tries to form the hydroxyapatite layer, and this is being observed in the cycle. But there are challenges. The melt quench driven glasses are not usually used for healthcare assist devices, particularly if I'm trying to look for the osteogenesis application. These glasses, especially the melt quench technique derived glasses, are not found to be useful. They are not practically useful. So we have to have the production through sol gel technique. And again, coming up with sol gel technique, it has the complex in chemistry as well as the reaction mechanism. This is one of the major challenge that we have, especially with respect to borate as a former. And second major challenge that we have is the degradation rate is very fast, especially with respect to these borate based BG glasses. And again, the mechanical strength compared to the silica, the mechanical strength is less. And again, as you know, this boron has a very less coordination number. Forming the 3D structures is very limited. So again, borate glasses, they do not play an important role. So the next most well-known former that we can use is the one which we also see in our tablets, whichever that has been synthesized. The tablet that we see, it has been written. For example, if I'm trying to purchase Dolo 650, if you see the chemical composition of the tablet, they would have mentioned it as paracetamol IP. I.P stands for inorganic phosphate. So when we go with the phosphate as a former over here we have, they are highly bioactive in nature, and they have higher and more controllable degradation rate compared to borate, and they have wider solubility in aqueous environment. They have flexibility in shape and composition. The ease of access to doping these bioactive elements are much more, and strong bioglass and bone bond, and they tend to stimulate towards the formation of bones, and they have reduced crystallization rate. And due to very less network connectivity, again, even here the hydroxyapatite layer is complete. And since we are trying to deal with a phosphate material, the possibility of forming highly porous material with large surface area is possible with respect to phosphorus. Again, the challenge is with respect to the synthesis. We have to go with the sol gel process, and the degradation rate is also very much quicker, and they have poor mechanical properties. So now here I would like to show you, actually the view is just, I just got only one pic where we had tried to synthesis a glass and we checked for its bioactive. Before getting into the bioactivity, we just wanted to check whether is there any possibility of formation of hydroxyapatite layer. So here you can see we had dissolved these glass into an SBF solution. SBF means it is called a stimulated body fluid. So it is just trying to have the fluids that whatever our body has, the same amount of fluids are being prepared. And those composition, when the moment when you place this glass, you are able to see these white layer that are being formed. These white layer that are being formed confirms that the glass is trying to release the hydroxy. It is able to form the hydroxyapatite layer. That is because we have maintained for that particular composition, we have maintained the low sodium to phosphate ratio. So it has started creating the bone, regeneration of bone. So this is where we were successful in demonstrating the first phase of the experiment. But when it comes to the cytotoxicity, we had failed in our experiment. This material was found to be much more cytotoxic. And further, again, due to some challenges or limitations, I did not pursue this problem further. But I am again curious and eager to pursue this problem. And if I have to uh, share that this problem, I was able to do it without, I was able to do this only because I had help from my friend. His name is Dr. Chetan. He is currently working as assistant professor in Jain University. His expertise is in the field of bioactive glasses. So we had collaboration and we worked on it, and we were successful in making this achievable in a different technique, that is by making use of the microwave technique. But not much more it was not much more efficient, particularly when we came up with when we came up with melt quench technique, we had failed. So we thought there could be a possibility of the hydroxyl region, which was found to be very less in the microwave synthesis. Then when we are trying to look at the industrial battle, especially with respect to the current trend is, we always try to see whether it is bosons or fermions. To keep it very simple, the bosons usually represents for photons, photonics, and fermions represents for the electrons. So now, when I say electronics, usually we come up with silicon chip. They are usually made up of semiconducting element, but today we are coming up with glass chip, which are usually made up with some transparent dielectric material. So with lesser thermal expansion coefficient than silicon. So this is one of the major thing that we are trying to see that is happening, especially with respect to the silicon technology. Well, the main replacement with respect to silica towards the glass is glass can be engineered for a flexibility, and they can be used for transparent electronics as well as flexible electronics. Whereas if you're trying to deal with silica, they're opaque in nature and they're rigid, and their application viability is limited when it comes to with respect to transparency or flexibility. Then, if I have to say with respect to the thermal property, glass is excellent to heat resistance, so that it leads to much more energy efficient designs where you need not require much more extensive cooling system. On the contrary, silica has lower heat resistance with high thermal conductivity than glass. So these chips, they become much more powerful, and they require much more heat, and thereby what we see here is when you are trying to look at the larger when you are trying to deal with the larger problem, it requires much more complex cooling systems, especially with respect to silicon photonics or silicon systems. So next, what we see is how do you transmit data? So today, the whatever the technology that we are trying to use, even today, if I'm able to deliver this lecture, it is because of the FTTH technology, that is fiber to home technology. So that is because of the optical fibers that we use. They are able to transmit the data using the light, which we call it as photons. So this is much more energy efficient, faster, and this is being used very extensively with respect to the communication system. But when you're trying to look at the silicon photonics, there are some, they make use of the electrons and electricity, especially if you look at the old telephone system that we had, or if you had experienced the dial-up connection, that was based on the copper technology, where we were trying to deal with electrons to transmit the data from one end to the other end. And now the next important factor that we try to see is when it comes to the 3D stacking part, because these materials, they have a very less dielectric constant. So this will enable glass to stack much more chips for improving the signal integrity. Whereas on the contrary, with respect to silica, the interchip communication might lead to high signal loss, and thereby it requires much more complex 3D integration system. So when it comes to the technology that we have, especially with respect to chipset manufacturing, glass is still in the lab level. It has not come to the market yet. Still, the experiments are going on, and as of now, since it's in the R&D level, the cost of manufacturing is also significantly high. So the investment has to be towards the glass chipset design, so that the product becomes much more cost effective when once it comes into the market. And when you look at the silicon, on the contrary, it is actually well established technology, silicon chipset, and we have we can see that they have been leaders for almost several decades, and the R&D part, especially with respect to silicon technology or silicon photonics, has been well established and well ahead. So further, when we come up with the durability, glass is inherent with respect to corrosion, and they are trying to prove that, but corrosion to the chemical environment. But however, when it comes to mechanical stress, they are highly brittle, and especially when you are trying to devise the portable devices, glass is not much efficient. That is where silicon rules with respect to the mechanical stress. So, especially if you are trying to look the next gen systems, we are, especially if you are trying to look at quantum computers, particularly for the ion trapping, glass is being used, and it has much higher fidelity rather than the silicon chips. And especially with respect to the consumer electronics, if I have to say, there are much more potential applications coming up with much more faster wearable devices, as well as flexible displays and smartphone devices, when it comes with respect to glass chips, if it is being established well. And these are the few key um, news articles that I have come across, especially when we have to see Intel had demonstrated test chip on glass substrate, especially it came up way back in 2021, and we have IEEE, which was trying to emphasize much on glass chip, which is going to be the key for the quantum architecture. And then we have Scott, where they are coming up with the glass based chips, and the entire, if I have to say, there is a team which we call it as class, which is called as quantum glass based photonic integrated circuits. And we have eForce.io, which is a company where they have received nearly $49 million for chipset, especially Europe, from the European Union. And they are basically working on glass based integrated photonic circuit devices. And even Apple, for that matter, they are also coming up with glass substrates. So if I have to say, India is also moving ahead with semiconductor technology for 2030, and nearly 9,600 crores are being invested for those field. If if there are if we can actually encash the glass science and technology towards that towards the electronics field, probably we can come up with much more efficient devices, and we can also come up with our own Atmanirbhar products for this, especially for the quantum computing devices. So before I conclude, I will try to just tell one small story. So the glass, as I was telling you, it had a Proto-Indo-European trait from its name. But how did we come across this glass? It is very interesting. I had an opportunity to visit a site which is in Madurai district, which we call it as Kiladi site. There I saw that this is called as mortar and pestle, which they were used to make earlier, and this is nothing but it was a furnace where they used to make the glass beads. And here I have taken few pictures of glass beads, and you can see all these colored glass beads that are being made. They are actually being made, and these were found in the excavated sites of Keeladi. And today, what we say, the famous Lysergus cup, this was actually it is being made by gold and silver nanoparticle. Actually, the word pudoke means, especially in Rome, it means it is emporium. So they used to come to a glass emporium, which was in a place called Arikemedu, which is currently it is in Pondicherry. So they used to call it as pudoke. So pudoke became Puducherry or Pondicherry. That's how the name also came across. This is what I came across, one paper, famous paper from Robert Brill, where he visited the Arikemedu site, and he said that there was a possible Indo-European trade, especially from Arikemedu site. So coming to the Indian connect, especially with respect to the scriptures that we have in the glass science. So there is a scripture which you call it as Amsubodhini. In that there is one chapter which describes about the relevance of glass. So it has mentioned Spatika, Ranjika, Guhari, Saikita, Sajikara, Daundika, Shalya, Viranji. If you are trying to mix all these elements up to a temperature of 300 kakshas, it leads to formation of glass that leads to Sahasra Jyotis. So, which means that they are talking about a glass which can increase the manifold of lights. It is nothing but it is the glass photonics that they have described way back in our scriptures. But we are still, we are still unable to identify what are these elements. Actually, Naga doesn't mean serpent; it means lead. So Saurika doesn't mean it is something made up of sun. It is called as gold. So there are few, they have coded it in such a way that we have to decode these elements, and then we may have to again do some R&D in these fields also, so that we can get to know what our ancients were trying to say. So metaphorically, they have described these elements, and it's a very interesting book. It is also available in archive.org. You can just check Amsu Bodhini to know more about the material aspect. You can just go through it. And there is one more Ayurvedic book which we call it as Rasajala Nidhi, where they say there is a statement where they say Bhargas, Subharghav, Kanakam, Hiranyam, Hemahantakam. So where they say actually Gold is red when melted, it leaves the saffron tint when rubbed on the stone. See, we are talking about the Lycurgus cup, where we see that there is a stained red stain or the pinkish stain or the ruby red or striking red glasses. But actually, these things were actually found even in our ancient scriptures way back in 14th century, sorry, way back in 3000 BC or 3500 BC. And even Kautilya's Arthashastra, which also speaks about the glasses which were made with respect to when they were tried to heat treat these materials with respect to 17 times or with respect to 33 to 32 parts of gold and silver, it leads to reddish and whitish elements. So this is from the Arthashastra point of view also. So one small thing that I would like to tell is, we expected when we tried to make one composition where we wanted to come across with a bone regenerating glass with respect to high porous density, we expected it to turn out to be amorphous in nature, but what we got is a polycrystalline material. So the crystallite size is almost closer by to 1 nanometer when we estimated using Debye-Scherrer method. So there is always a transition from glass to ceramics. So what I infer from this is, science acknowledges failure as an experience leading to new perspectives. So coming up to the last slide, what I would like to do is, whatever I'm today, it is because of my family. So I acknowledge my family, my institution. He is my guide, Dr. Rajshekhara KM. He is my co-guide, Dr. Rajaram Krishna. He is also his postdoc supervisor, Jakropong Kyamko, and Professor Venugopal, Dr. Jagannath, Professor R.V. Anvekar, and they were my doctoral committee members. They were my advisors, especially Professor B. Iraya and Ayachit. Without them, I am nothing today. They have been continuously monitoring me and trying to give me much more insights, especially with respect to glasses when I was working in the melt quench technique. And here we have Sudhakar Reddy as Dr. Sudhakar Reddy as well as Dr. Shivshankar Reddy, who gave me insights when I was working in the field of microwave technique glasses. So these are my teammates, Dr. Vinayak Pattar, Dr. Venugopal, Dr. Sanjay. Without them, I wouldn't have zeal, especially to perform, to come up with the glass science. They have been supportive to me even during my tough times. And they are my gurus who gave me, especially Professor Sheshadri, Dr. Raghutam Rao, Dr. K.T. Vasudevan, Dr. P. Nagaraju from National College. They have given me a lot of facilities to perform research in National College, Jayanagar. And here we have Dr. Shyam Sundar, Dr. Anandavardhan, Dr. B.S. Dwaraknath, Dr. Venkatesh N.S. from Indian Academy, who have supported me in my tenure in Indian Academy, especially when I was trying to work on the project in especially with respect to uh, glass science in microwave assisted glasses. And here we have Professor Rakesh SG as well as Dr. Hariharan Hen, who have supported me to pursue my research further from Sir MVIT. I acknowledge them, my humble pronouns to them, and I also acknowledge the stick DST, as well as I acknowledge all my friends who have helped me in shaping my career in glass science. So the quest, especially with respect to glass science, still continues. These were the glasses made by me during my PhD. I am signing off now. Thank you. Thank you for your patience hearing. And if there are any questions, please, you can ask. You can unmute and you can ask. Thank you. Actually, 1 minute. I will first go through the questions which you have posted.
Yeah.
I will try to address them. If there are any questions to be answered, if there are any questions from the audience, first I will try to answer them. They can unmute and ask if required. Then I will try to go with the messages. Any questions from the audience side? Okay. So your one of your question is which was posted here. It was like, what message would you give to students and budding entrepreneurs to stay motivated and explore opportunities in science, technology, and innovation? Thank you. I'm not sure who has come up with this question, but it is really a very interesting thing, because we are moving towards the Viksit Bharat 2047. So, if I have to say, there are a lot of misconceptions that are being told that the R&D budget is very less when it comes to when it is being compared to China, where they spend nearly 3% for R&D. But if I have to say, nearly 10% of our GDP has been spent, especially with respect to Atmanirbhar Bharat scheme. Why don't we make use of our R&D, especially, why don't we come up with the product based solution and try to make use of the opportunities that are available? That is one of the important thing which I would like to tell. And again, as I was speaking about the chipset manufacturing, particularly with respect to the device manufacturing thing, we were focusing on silicon photonics a lot. But if we can explore somewhere related to glass chipset design, I think there is an opportunity for us to grab some more uh, funds from the government, especially with respect to the semiconductor industry by 2030. So I would rather tell students to start questioning with themselves, come up with one idea, and try to develop that idea, try to stay with that idea forever. For me the idea is with respect to glass. For others, it might be with respect to something else. For some, it might be with respect to the nonlinear optical devices. For some, it might be with respect to the silica. For some, it might be with respect to reduced graphene oxides. I mean, since my domain is with respect to science and technology, I am just sticking with that. But they can further, if they have some idea, let them stay with that idea. Let them continue with that idea. Let them work for it. Let them try to find some grants for it. DBT, especially for students who are working in biotechnology, they have enormous funds from Department of Biotechnology. So they can also make use of those funds. Actually, they have to come up with that idea. That's what is my message to them. So the second question that you have asked is, what do you see as the future of glass in India, especially in architecture, energy efficiency, and sustainability? Especially when it comes to architecture, I had told, particularly with respect to the glasses for uh, glasses which can be used as smart windows. So that is, and in fact, most of the buildings that you're trying to see, facades, glass facades, they come with respect to these. Um, these materials. So future of glass is always there. It cannot be told that okay, the glass science is, there is an end of era with respect to glass science. And coming to energy efficiency, no doubt, this solar cell, especially when you're trying to deal with, we have somewhere where we can come up with stained glasses or the plasmonic. Today they are working on perovskite glasses, perovskite materials. Probably tomorrow we can come up with plasmon assisted devices, which is much more. I didn't, since you told me to have it in the popular talk session, I didn't cover the surface plasmon resonance aspect of the materials. But again, even when you're trying to deal with gold or silver nanoparticle embedded systems, they try to deal with plasmonic systems. Even they have much more energy trapping efficiency. And especially with respect to sustainable goals, we have a major impact when it comes when you are able to come up with much higher efficiency, especially when you are trying to deal with plasmonic assisted devices. And coming to your question that you had asked me is with respect to what are the merits and demerits when it comes to glasses, if I'm not wrong, in future. So glass, as such, it is the low cost technology where you need not invest much for it. And coming up with the especially with respect to the quantum chipset design aspect, we have a lot of challenges, especially with respect that can be addressed with respect to glass science. And coming with respect to the biomedical health sectors, we have the especially with respect to the osteogenesis application. Coming up with these glasses, especially bioactive glasses for osteogenesis application, they can if, for example, if the plate has to be replaced, you have to do surgery once to place the plate, and again you have to do surgery to remove the plate. But when you are coming up with these bioactive glasses, you just need to place them. You need not do surgery twice for it. So in a way, it is going to be much more meritorious. And I don't find anything demerit with respect to glass science, because it can be melted, remolded, reshaped once again. So this is what my takeaway from this. Further, are there any other questions, Ramkrishna? Or did I take much more time?
No, sir. It was good. Mahesh, sir?
Yeah. I think he left.
Okay. So I wish all the best for Dr. Abhiram, and
Thank you.
it was a indeed, a very good
Sir,
presentation.
Yeah.
your
Yes,
presentation
ma'am.
was. Sir, can you hear me?
Yes, ma'am. Yes, ma'am. You are audible.
Oh, your presentation is very good, sir. Actually, I'm
Thank
so
you, ma'am. Thank
inspired to listen to your presentation, and I,
thank
I
you.
felt like you have done a lot of work in related to glass, sir. Especially the way you portrayed it. It was like I was in the glass lecture in a very high standard institution. So same
Thank
like this, if everybody works, I think our country can move forward in a very good way. It's
thank you,
really
ma'am.
very
Thank you.
informative and is socially so responsible, your presentation.
Thank
Thank
you,
you
ma'am.
so much,
Thank you.
sir.
Thank you, ma'am. Thank you.
So, one small question I have that
Yes, ma'am.
I will ask. Can I ask now?
Ram
So,
Krishna.
this property of the glasses that you have portrayed related to civil engineering.
Mm.
So mostly thermal, thermal is more right. It is thermodynamic in nature. It conducts lot of heat in terms of glazings.
Oh, you're talking about the facades, the smart
So if
windows.
you put glazings,
Mm.
yeah. So how we can go forward with that to reduce the temperatures? Because we feel that compared to the stone, granites, marbles, glasses conduct lot of. Because we wanted a material outside if it is hot, inside it should be cool. So it should be different. So how
Yeah.
is a glass will be helpful in that way? Any possibility?
So certainly, ma'am. One thing which I would like to highlight is, the major heat that we are trying to see in glass is because of it is usually because of the uh, UV rays. Actually, normally in buildings, what we see is the high intense UV rays are being absorbed by the glass. Glass is a very good absorber of UV rays. So we can see that by replacing them with glass, you can reduce the heat naturally. And coming up with the coatings that we have, especially with respect to the liquid crystal based coatings, the pneumatic phase to liquid crystal, once the heat falls into the material, they tend to change their orientation. So when they change their orientation, the heat gets absorbed on that film, and it leads to coolness inside the environment. This is being demonstrated, ma'am. There are some firms like Isotherm firm where they have come up with glass packets for these solution. The solution is already been there in the market.
Okay, so thank you so much. Thank
Hope I
you.
answered your question.
Yes, clearly.
Okay, thank you. Any more questions?